Okay, so I'll just give you a broad introduction, and I decided to make the title look a little catchy. So the title is The Many Mysteries of Space and Time, or What Black Holes Have to Do with Boiling Water. Okay, so there is some some understanding that we have about black holes, which essentially have to do with theory of strong gravity. And it turns out, over the last few years, it has been realized, last few years as in the last 6 or 7 or 8 years, it has been realized that several aspects of black holes actually mimic real life phenomena of things like boiling water and condensed matter physics, entanglement and stuff like that. And it is believed, today people believe, I mean there is some faith which is emerging, that probably all these things are interrelated, and probably understanding black holes, when I mean black holes I mean certain classes of black holes, not all black holes. So black holes also exhibit things like, you could study things like entanglement in quantum systems in your laboratory by exploiting some properties of black holes. I mean, this is not very new really, in the sense that, apart from, that black holes are objects from which light cannot escape, that is the most classical definition of black holes. And it turns out that there are things called acoustic black holes, where light is replaced by sound. Okay, so there can be things like that. So these are called acoustic black holes, but I will not get into that. But what I'm saying is that the phenomenon, the physics of black holes are quite intimately related to various things, and it is now starting to emerge a very important understanding that probably the tools or techniques to understand black holes might be very similar in gross effects, not in microscopically, but macroscopically might be very similar to what we see in day-to-day lives like boiling water. So that is what I'll try to tell you, and I'll try to impress upon you the very intriguing features of black hole space-times. And we'll start here. Okay. So space and time, once you think of space and time, and it reminds you of the night sky, okay, because that is the natural place where you look at the beauties, the mysteries of the universe. And if you look at a clear night sky, you see all these stars and constellations and galaxies. If you're on the top of a mountain, you could actually see the Milky Way. And then you start wondering that, so what are the forces of nature that create these objects, or what are these, how are these objects made of, what are these objects made of? And there's something, anyway, so this is a typical picture of a night sky. And when you look at the night sky, when you look at, when you look around you on a clear sky, it happens that there are mysteries of nature called black holes lurking here and there. I mean, you cannot really see them by a telescope, but there are specialized means to observe these things. And in the night sky, along with your stars, your galaxies, your Milky Way, etc., etc., there are black holes which are also present. Okay, and understanding the nature of space and time has been one of the most fundamental endeavors of science, and the motion of heavenly bodies have actually fascinated the best minds over the centuries, starting from Newton, Galileo, Newton, Copernicus, all the way up to Einstein, etc. And probably, as people say, I mean, this is just a folklore, that modern physics started when an apple fell on Newton's head more than 300 years back. Well, we don't know whether the story is true or not, but at least that's the folklore. And Newton discovered the fundamental laws of motion of material objects, which are now called as Newton's laws of motion. And in the process, he discovered the laws of gravitation as well. Okay. And Newton's laws, you would know that these are invariant under what are called as the Galilean transformations. Galilean transformation is just shifting of your coordinate system without doing anything to the time. And this was enough to describe mechanics at the observable scale. What I mean by observable scale is what you look at day-to-day life in tabletop experiments or in football fields, motion of a football when kicked and things like that. And then at the observable scales 300 years ago, when the microscope was not really discovered, and this was probably enough, and everything seemed to fall into place. But in another major development, and this was actually the most important thing that happened after Newton, in the 1800s, Maxwell, Ampere, Oersted, and others formulated a theory of electromagnetism, that is, a unified theory of electricity and magnetism, which did not have Galilean invariance. So Newton's laws had Galilean invariance, Maxwell's theory did not have Galilean invariance, and this led Einstein to suspect about 100 years later, 100 not, maybe 70, 80 years later, this led Einstein to suspect that Newtonian mechanics is possibly, there is some flaw in that, and he formulated what is called a special relativity, a theory in which space and time was unified. Okay, so unified, like a unified description of space and time. Basically, one thinks of time as one of the coordinates in a four-dimensional world called space-time. So that was special relativity. Okay. And later on, in 1916, exactly about 100 years ago, back from now, Einstein generalized his theory of special relativity to general relativity that describes there's an intriguing thing, the interaction of space and time with matter. As in, a theory of gravity. And the genius of Einstein, actually, he realized that space and time and matter, they cannot be thought about separately. Basically, they interact with each other, and the matter is determining the nature of space and time. So that's what he thought, and this is indeed our biggest tool to understand the physics of the universe. Okay? And general relativity is, of course, it's a fascinating theory, a theory that has undergone several precision tests. And of course, as in any theory, it is not, you do not know whether it's right or wrong unless you have actually experimentally tested the theory. And there are many precision tests of general relativity that have been done. And as I'll talk about, the most recent one being in 2012, called the Gravity Probe P experiment by NASA. And even now, people try to devise experiments that test general relativity. And as of today, no test has actually violated the principles of GR. So the day it does, that will be the end of GR, but it doesn't seem so. And it looks like, as in science, there is nothing called a permanent thing. Something keeps changing, some other theories will come. But GR, as of now, is a very solid theory whose experimental tests have been absolutely, precisely, the measurements have been precisely made. And we believe that GR could eventually describe the origin of our observable universe. So the universe, which contains like trillions of heavenly objects and is supposed to have started from a Big Bang, although that is also, there is some debate in the community about the exact nature of the origin of the universe, etc. But one currently estimates from cosmological observations, the universe is currently estimated to be about 13 billion years, and one of the most important inhabitants of the universe, or the most important inhabitants of the universe, are stars. And these are massive fluid-like objects which are held together by their own gravity. And a star is formed as a result of what is called as a gravitational collapse. And these are things that you could actually work out on pen and paper. It's fascinating that things which are happening at the scale of the universe, you could actually write down formulae to understand, to decipher the meaning of these processes. And a star is formed as a result of gravitational collapse when a huge amount of gaseous matter, it starts collapsing under its own gravity. And once a stellar core, so it starts forming a core, but once it is dense enough, it starts nuclear reactions inside, and then it provides enough energy to prevent that gravitational collapse. So there is some kind of an equilibrium that is reached. So this equilibrium, it's also described by what is called as the Tolman-Oppenheimer-Volkoff equations. You could also write this down as some kind of an equilibrium condition in fluid dynamics and study the same. So that's a different field of astrophysics that people work on. So essentially, once the stellar core, so when it is collapsing, when the stellar core is dense enough, nuclear reactions are triggered, which then prevent further fall, and some sort of stability is reached. But what happens? What happens when the fuel inside the star gets over? Because the fuel is not everlasting. It might take a billion years for the fuel inside the star to get over, but what happens when it gets over? Well, depending on the initial conditions, and these are very, very tricky things to actually calculate. And let me tell you that, I mean, these processes, I'll show you in the slides how they, I mean, what is our current understanding, but they are enormously difficult to calculate, and people resort to very, very high precision computer simulations, etc., to actually understand these processes. But our current understanding is the following, that once the fuel inside the star gets over, then depending on the initial conditions, a star might evolve. If it's a small star, it might evolve into a dwarf star, or a neutron. If it's a big star, it might evolve into either what is called as a neutron star or a black hole, primarily under the forces of strong gravity. I'll just explain what I mean by this. So this is roughly a rough picture of how stars evolve. And essentially, there is a stellar cloud which collapses and forms the stars. And the stars, they radiate because of the nuclear energy that they're generating at the core. And then the small stars, there's a sequence. They actually, after some billions of years, they'll form into a red giant. I'll explain to you what this is. After some time, they form a planetary nebula where a huge explosion takes place, and much of the star is ejected out, and then it remains as a white dwarf. If the star is bigger, then what happens is that the same thing, the same sort of sequence evolves, repeats. It forms what is known as a red supergiant. Then it forms a supernova. There is a supernova explosion, and then again, depending on the initial conditions, which are extremely well predicted by Einstein's theory, it might actually form what is known as a neutron star. It might form what is known as a black hole. So this is roughly how the evolution of stars occurred. And if you ask, like, what would happen to our sun, maybe in a billion years, the sun would actually follow the upper sequence. It would become a red giant, engulf the whole, Earth and everything, and then finally it will die as a white dwarf, and that's the end of everything. Okay. Sorry. A neutron star is a very massive star which has, densities roughly 10 to the power 28 grams per centimeter cubed, and the radius of a neutron star is roughly around 11 to 20 kilometers. Okay. Okay, so most of the stars, so how does this work? So this is a very, very elementary type of way to say it. So most of the stars in the universe, they convert hydrogen to helium by nuclear fusion. Initially, as I told you, the outward pressure of the fusion balances against the inward pressure of gravity. You could just work this out. This is a very simple exercise, and the equilibrium condition is what is known as the Tolman-Oppenheimer-Volkoff equations. But once the fusion stops, that is, once the fuel gets over, then gravity overwhelms and it compresses the star, and it becomes smaller and tighter. Now, the temperature. Now, once the star is contracting, it's a thermodynamic process. The temperature, you could calculate and show that this increases, and eventually it reaches such a high level that the helium fuses into carbon. Now, the helium burning, it might be gradual or it might begin with a flash, and these are things that NASA actually observes. I mean, these are, I'm not making this up, these are things which are actually observed. And the energy produced by the helium fusion causes the star to expand to many times its original size, and this is what I call as a red giant. This is a very, very simple type of thing. I mean, the actual computations are somewhat more involved, but at least this is what happens. Now, these stars, as has been observed, the red giants, they spent approximately a few thousand to 1 billion years as a red giant. Eventually, what will happen? The helium in the core will also run out, the fusion will stop. Again, the gravity will overwhelm and start compressing. And then the star shrinks until a new helium shell reaches the core. Then again it will start burning. Then typically, when the helium ignites, it can be shown by simulations, or even theoretically one can show that typically at some stage what will happen is that the outer layers of the star will be just blown off, okay, into clouds of gas and dust. These are known as planetary nebulae. And the core continues to collapse, and that's about it. It then forms a white dwarf, and that's it, the star dies. So all the stars that we are seeing today, at some point of time, they'll die a natural death. Okay, they might either become a white dwarf star, they might become a neutron star, or they might become a black hole. In fact, in neutron stars, actually, as he asked the question, I mean, there is also another very important thing that happens, as Chandrasekhar had got his Nobel Prize for this discovery. So there are quantum mechanical effects inside the star, which also, which also sort of contributes to the balancing equations. Anyway, let's not talk about that. But then, for large enough stars, so these are for small stars. For large stars, a similar sequence of events take place, and the formation of a black hole or a neutron star happens. And what I wanted to impress upon you is that from all this, you can see that black holes are essentially a phenomenon of very strong gravity. When gravity is so strong that it collapses, objects to unbelievably small sizes, that is when the phenomenon of black holes occur. And therefore, typically, you do not talk about black holes in usual gravity. You talk about black holes when you have very, very strong gravity, as in collapse processes, etc. But now, let me just tell you some fun facts. What about, you might ask that, okay, so gravity, but so what about, can we describe quantum processes during this collapse and what happens? Let me tell you that this is actually the biggest open question which people do not know. That what is a theory that can unify both quantum mechanics and gravitation? So that the answer is not known. Okay, but let me just tell you a few things. See, just to be heuristic and give a hand-waving argument, if you want to reconcile quantum mechanics and gravity, let's think of the constants, the physical constants which appear in these theories. Quantum mechanics must have h cross, h bar, Planck's constant. Gravity must involve the Newton's constant, because those are the fundamental constants which appear. And also at some point of time, the speed of light also has to be involved, because this is gravity, and special relativity teaches us that that's one of the fundamental things. So if you look at it this way, you could actually multiply h cross times g, divide that by c cube, and you will find that the square root of that has a dimension of length. So starting from these three fundamental constants, h cross, g, and c, I could cook up something which is a dimension of length. If you actually calculate this quantity, you know what is h cross, what is g, and what is c. It turns out to be roughly like 1.6 10 to the power minus 35 meters. And we believe, it's just a belief, that gravity actually becomes important at this length scale, which is also called the Planck scale. So this is a heuristic argument, but that's how nature works. I mean, very simplistic logic that, okay, so we have three constants. If I want to define a length scale in the theory, how do I define a length scale? Well, a length scale must have at least the dimensions of length. Out of these three constants, how do I make up a dimension of length? There's a unique way. The unique way is simply this, h cross g by c cube. This was written down by Planck. It's called the Planck length. And it is believed that at 10 to the power minus 35 meters, so that is the length scales at which gravity becomes very, very important, very, very strong. Okay, so now there's an important length scale in gravity, another important length scale, which is called the Schwarzschild radius. I'll tell you what that is. But for the moment, you note that I could actually form, suppose if I'm given an object of mass m, classically, forget about the h cross, with g, m, and c, I could form another length scale called the Schwarzschild radius, which is gm by c squared. Up to now, it's fine. So the first one was, the Planck length involving h cross, g, and c. There was no mass anywhere. The second one is g, m, and c. There is no h cross anywhere. But you also know that there is another important thing in quantum mechanics, an important length scale called the Compton wavelength. And this Compton wavelength, in quantum field theory, the Compton wavelength is actually a very important thing. And this wavelength, the Compton wavelength, is given by h by mc. Okay, this you have studied. But now, if you equate, if I just be very naive and I equated Ls with Lc, sorry, this actually should be not lambda, but Lc. I'm sorry, there's a typo over here. So Lc is equal to h by mc. If you equate the two, you get the Planck mass. You get an expression for the mass, something which has dimension of mass in terms of h cross c and g. And then, if you put m equal to, you call that the Planck mass. If you put m equal to m Planck, you find that the Schwarzschild radius equals the Compton wavelength. So this is a somewhat heuristic, but maybe you can think about it more, that what what is the relationship between quantum physics and gravity? Well, quantum physics and gravity essentially means that you are dealing with a mass called the Planck mass, okay, which is that h cross c by g, okay, and you can see that from here the Planck mass is some huge number, it's some 10 to the power 32 or something kg or something. And if you put, if at a mass scale, at the mass scale where our typical mass is of the order of the Planck mass, the Schwarzschild radius equals a quantum. So that is something which tells you how these things are interrelated. But of course, this is a very, very heuristic thing, and a precise, theory of gravity which incorporates quantum mechanics have not been found. Maybe one of you could help in that. Anyway, so about 100 years back, in 1916, Einstein realized that the effects of gravity, and this is a very important thing, it cannot be understood in the framework of Newtonian physics. So he first formulated, because he realized that there was something which was going wrong, that is, that Galilean invariance versus Lorentz invariance, so that was something which was not being able to fit into the Newtonian theory. So he formulated the special relativity, which is a theory that unifies space and time by two postulates. The principle of relativity, which tells you that all physical laws are invariant in all inertial reference frames. And secondly, the most important postulate was that the speed of light in vacuum is a constant in all inertial reference frames. So with these two postulates, special relativity is all about the invariance of an interval, and this statement actually contains all of special relativity, that you take two events. An event is happening somewhere in space at a point in time. Take event 1, take event 2. Suppose the spatial displacement between the events is in 3 dimensions is dx, dy, dz. Suppose the spatial displacement in time is dt. I've put c equal to 1. Actually, there should be a factor of c squared over here. It's a bad habit to always set all constants to 1. But in any case, Einstein's theory, the basic thing about Einstein's theory is that this particular invariance, this particular quantity which you call as the interval, is the same for all inertial observations, and this contains everything about special relativity. This one line. Okay. Now, special relativity, of course, there are various things about it. So this you could talk about Lorentz transformations, length contractions, things I'm sure, time dilations. The special relativity finds usage in things like cosmic ray showers and predicting lifetimes of pions, etc. It finds usage in global positioning satellite systems, etc., etc. And those are all very well known. But the next step that Einstein took was to generalize this theory to what is called as general relativity. Okay, and I'll just give you one small example which would sort of set the stage for the understanding this. Think of a body which is falling under gravity. Okay, so suppose a body is falling under gravity. So its equation of motion is d2x dt squared equal to, I forget about the mass I've set to 1. Okay, so suppose this is the case. But now suppose I decide to be crazy and I decide to introduce a new coordinate, call it eta. I say that, okay, I'm not going to measure x and t, but I'm going to use a very, I'm going to be a completely mad person, but I'll introduce a coordinate which is x minus half gt squared. I call that coordinate as eta. I introduce a linear combination. Okay, and then if you notice, then in terms of this coordinate eta, okay, d2 eta dt squared equal to 0, which means that in this coordinate eta, that is, if you have gone to an accelerated frame of reference, you could actually negate the force of gravity. Okay, and conversely, effects of gravity can be studied by transforming to accelerated coordinate systems, and this was the main contribution of Einstein. So, which tells you that, suppose if you look at it this way, suppose if things move in the same way in a gravity field as those in a reference frame accelerating upwards with the same magnitude. So an observer who is inside cannot by any experiment determine whether he is actually under the effect of gravity or whether he is actually in an accelerated reference frame going up. But if that is the case, then what Einstein said is that if that is the case, then mathematically I could actually describe everything about gravity by going to accelerated reference frames. And that is called the principle of equivalence. Okay? And this is like, this says, the principle of equivalence says that just like locally gravity and acceleration are indistinguishable, similarly effects of gravity can be simulated, it can be studied by transforming to non-inertial coordinate systems, and general relativity is a theory of non-inertial coordinate systems. Okay? Now there is, okay, before that, I mean, there is one question that, you know, many people ask me, like, what about the speed of light in a non-inertial coordinate system? Well, in a non-inertial coordinate system, the speed of light can be anything. Okay? The special relativity tells you that in inertial coordinate systems, okay, the speed of light is a constant. What about, what is the corresponding statement in non-inertial frames? The corresponding statement is that if you are in a non-inertial, there is an accelerated frame, then you could go to a locally inertial frame in which the speed of light is still c. But otherwise, it could be just about anything. I mean, you don't, that question doesn't really make physical sense. When you talk about measurements and observers and things like that, you always talk about inertial coordinate systems. But in any case, at the end of the day, GR is about solving the Einstein's equation. This is about the only mathematics that I'll show you. This is, the left-hand side is called the Einstein tensor. The right-hand side, the Einstein tensor, okay, this G is capital G. This capital G is a Newton's constant. The left-hand side is a quantity which is entirely determined by space-time. And the right-hand side is a quantity, this T mu nu is a quantity which is entirely determined by the matter content. Okay, it's called the stress energy tensor. And there is an additional term which has become very important these days after the advent in string theory. People call this as ADS-CFT correspondence. This is called as the cosmological constant. So these are the Einstein's equations. And in 4 dimensions, so there will be 16 of them. And the solution of this Einstein's equation is what is operational GR all about. For example, I could give you some form of T mu nu. There is the energy momentum tensor, which is the matter content. And I can ask you, what is the G mu nu that will satisfy these equations? So that is the type of questions one asks, and there are several exact solutions for these equations which are known. So just to summarize, this is describing the interaction of space and time. The left-hand side is entirely determined by space-time. The right-hand side is entirely determined by matter. And this equation determines, therefore, the simple-looking equation determines, therefore, the interaction between space-time and matter. And you see, this is a coupled equation. You cannot change one and not change the other. And this mu nu, just to, I mean, they run over indices 1, 2, 3, 4, 0, 1, 2, 3. 0 is the time, 1, 2, 3 are x, y, z. Okay. So this is basically how people write that equation. In GR, you might see, you know, this is the analog. Remember, we wrote down this ds squared for special relativity. There the G mu nu was minus 1, 1, 1, 1. In GR, this G mu nu can be whatever. I mean, it's determined by the matter content. And then this is again, you know, I just wanted to show you because, you know, you should not go away without at least looking at these things. These are called the Christoffel connections. You determine them, and from them you calculate what is known as the Riemann tensor, which is derivatives of the Christoffel connections. From there you calculate the so from here you calculate the Einstein's equation by a suitable contraction. And one of the most celebrated solutions of Einstein's equation is what is called as the Schwarzschild vacuum solution. So I told you that you give me a T mu nu, that is an energy momentum tensor. Can I construct a G mu nu which will satisfy the Einstein's equation? So Karl Schwarzschild, very shortly after the discovery of Einstein's relativity, he discovered this solution. Notice that the coordinates are t, r, theta, phi. Over here t is the time, theta, phi are angular coordinates, r is a radial coordinate. But because the space-time is curved, you don't think of r as a distance, it's some coordinate. Okay? And over here, apart from this, enters this fellow m. This is called the Schwarzschild mass. So this describes a solution to Einstein's equation, where in the whole universe there is only one single mass, a point mass m, sitting at the origin. So you might ask, then how is it relevant? There is nothing else in the universe or what? Well, these are just models. And very, interestingly, many of our galactic structures can actually be, studied by using these models, because you can show that when you are a little bit away from that mass, the general relativistic effects are very small. So this is actually enough to consider. This metric is just enough to consider near the mass m. Now, if you notice over here, there is something very, very fundamental which you might suspect that what happens when r equal to 2m. When r equal to 2m, this blows up, this goes to 0. And more importantly, when r is less than 2m, this sign changes into a positive. This sign changes into, this should be a plus. This should be a plus, I'm sorry. Okay. This sign changes into a positive. This sign, which is actually a plus, would change into a negative. So space becomes like time, time becomes like space. But actually, there are various, the calculations, you could go to different coordinate systems and actually show that there is really no singularity at r equal to 2m. What do you mean by a singularity? A singularity is something, some physical quantity blows up. Physical quantities in special and general relativity must be scalars. They cannot change under coordinate transformations. Scalar quantities that you calculate from here, if you calculate what is called as a Ricci scalar, you find, or if you calculate what is called as a Kretschmann scalar, all the scalars calculated from this metric, they blow up only at r equal to 0. At r equal to 2m, nothing goes wrong. But r equal to 2m is a very, very important point. It's a very, very important point in space. It is called as the event horizon. Namely, if an observer falls into the black hole, that is crosses r equal to 2m, there is no way he can come back, because you can show that his future uniquely points towards the center of the black hole. Okay? So there's a lot of physics associated with this, and if you are interested, you might look it up later. But this was the first solution of the Einstein's equation that was discovered by Karl Schwarzschild, I think in 1917 or something, 1918, whatever it is. But this is, so this is called as a mathematical black hole. It has an event horizon at r equal to 2m. If you put in the factors of c, g, etc., that will give you the Schwarzschild radius that I talked about before. I've actually set also, this is like 2gm by c squared r. I've set all the constants to be 1. As I told you, that's a bad habit that we have. But if you put in all those constants, that's actually the Schwarzschild radius. The Schwarzschild radius, now just to give you an idea, the Schwarzschild radius of the Earth is about 9 millimeters. Which means, I just showed you that 2m by, you calculate the mass of the Earth, put in the factors of g, c, blah, 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 and you would realize that the Schwarzschild radius of the Earth is 9 millimeters, which means that if the entire mass of the Earth could be shoved into a 9 millimeter radius sphere, the Earth will become a black hole. Okay? And the Schwarzschild radius of the Sun is about 3 kilometers. But such small black holes, even if they exist, they are almost impossible to detect. And the best bet is with more massive objects. And in early 2001, it was announced that the data from the Chandra and the HST telescope perhaps provide the evidence for the existence of black hole event horizons. Harvard announced the discovery, and this Chandra and HST, these two Earth orbiting telescopes observed matter around sources that eventually disappeared from view. That is, the black hole ate them up. It sort of fell into the black hole. And as I told you, something which falls into the black hole can never come out. And that is basically it. And this observation, NASA said, it points to the event horizon. And Chandra observed X-ray emissions from 6 such candidates. Hubble observed the pulses of light from the galaxy cluster Cygnus X1. These came as clumps of hot gases. They seem to disappear around a candidate black hole. So that was an indirect observation, because otherwise you cannot really see what is a black hole. So now, suppose, just imagine a cloud of interstellar matter. So things are moving around in the universe. Suppose a cloud of interstellar matter passes a black hole. The black hole can accrete. That is, because of its strong gravity, it pulls it in, and as the matter is pulled in, its energy increases and it becomes hot. This will ionize the matter, which will then emit X-rays. Such characteristic X-rays have also been seen in many cases, and it is now believed that the center of all galaxies might be supermassive black holes, including our Milky Way. Okay? Although there is no direct evidence for that, but this is the belief. So now let's try to reconcile whatever we have said from the point of view of GR. As I told you, GR, space, time and matter form a coupled system. As in, matter tells space-time how to curve, space-time tells that curved space-time tells matter how to move. So when you put some matter, it curves the space-time, and that curved space-time in turn makes the matter move. So that's a coupled system. And in GR, you use the notation of a space-time metric. This is what I told you. This is the analog of the four-dimensional distance. The Schwarzschild solution at large distances, if you take very large distances, the Schwarzschild solution will just become a flat metric. So these are all consistent things. And just to tell you that in general, when we do GR, a static spherically symmetric space-time, just remember this will have a metric of this form, and given such a metric, you could calculate the Christoffel connections, which I told you before, and you could actually also calculate the equation of motion of a particle in the gravitational field determined by that metric. And that equation of motion looks like this. So you can see that this is like an acceleration, and this is like the force term, d2 x mu t lambda. Lambda is some kind of a parameter, and these are the Christoffel symbols which enter. And in flat space, when there is no gravity, this gammas actually disappear, and it just gives you the equation of a straight line. So these equations, these are called geodesic equations. So geodesic equations determine the behavior of particles in a given space-time. Now let me just go a little bit into what GR can tell us about galaxies, because again there are some very, very fundamental questions which remain unanswered to the day. Or maybe we can ask the question, is there any relevance of GR at the galactic scale? Because I told you that GR is relevant at Planck scales. What about galaxies? Galaxies are huge things. Is there any relevance of GR? Well, it is, because see, this is one of the most intriguing questions that have still not been answered. If you look at the rotation speed of stars in a galaxy, you would think, you can observe the stars moving around in the galaxy, and you would think that the rotation speed should fall off as a Keplerian law, if Newtonian mechanics is correct. Newtonian mechanics is correct if Newtonian mechanics is valid in this situation. But what people observed in 1930s, and it's still not answered, is that the rotational speed of stars, this is the radius from the center, this is kpc is called kiloparsec. 1 parsec is about 10 to the power 16 meters, so astronomers use the word, they cannot really write in meters, and then you'll have huge numbers. So 1 kiloparsec is about 10 to the power 19 meters. So when you are going away, actually the rotation speed does not fall, it flattens out. And nobody knows why. And the conjecture, the reason people say that it flattens out is because of the presence of what is known as dark matter. And this is one thing in which a lot of work is going on, and the flattening out of galaxy rotation curves is something which is still not understood. Now let's come to the other situation. So this is one unresolved question, and maybe we believe that maybe GR has some answer to that, but that's at a very nascent stage. And there is another thing, that suppose suppose there is a massive object over here. This massive object will curve space-time. Suppose a ray of light passes, close to that massive object, that ray of light actually should deflect like a material particle because the space-time itself is curved. And the important questions, okay, so this is one important question about this thing. And this is another thing that is really well studied in GR, and how GR deals with these issues about the galaxy rotation curve or about the bending of light is understood in very, very specific situations, but the full theory is not complete. Now, so this is one, just I wanted to show you some results that we have from a GR approach, which is actually quite new. And so we calculated by using some GR techniques the circular velocities in the galaxy, which are NGC 4395, and just to show you that some predictions of GR can actually come very close to matching with the experimental data, although it's not very clear, the full thing is not clear. Okay. This is now coming back to the issue of the bending of light. This is a telegram which was sent by Sir Arthur Eddington after they actually verified that this bending of light takes place. This was in 1921, so there was a solar eclipse, and during the solar eclipse they could see the stars behind the sun, and because of the bending of light, so the stars were actually seen at a slightly different place, and they precisely calculated that and found exact agreement with what Einstein had predicted. And this is the telegram that he sent to the Royal Society after that. And when Einstein was asked what he would have said if this was not correct, if this was not seen, he said, I would have felt sorry for the world. Okay. So now I told you that these are the particles in a gravitational field can be described by geodesic equations. Geodesic equations can be used to study the motion of all material particles, including massless ones, and even these show deviation from straight lines, that is the bend. Thus a massive gravitational body can also act like an optical lens. How does it work? Well, gravitational lensing is actually one of the most dramatic phenomenon, most dramatic demonstrations of GR in the cosmos, and it also might be very important in establishing the behavior of galactic physics. Theoretically, the description of gravitational lensing requires a calculation of the bending angle of light in a given space-time metric. The question is, what is that metric? And what are the lensing phenomena that we have to understand? So this is roughly the situation. You see, there is an observer over here, and this is an object. Because of gravitational lensing, actually the object can be formed. There might be two images of the same object, right? Just by usual optical arguments. And when the source, lens and observer are aligned, then what will happen? You would actually see a ring, isn't it? When the source, the lens and the observer are all aligned, so from all over the light can bend and come to the observer, so you actually see a ring. And those are called as Einstein rings. And this is an example of an Einstein ring. I forget the name of the galaxy in which it was seen. But actually, I mean, these, by the way, these rings are, you cannot see them with the naked eye, and these rings are very, very short-lived. That is, when three objects are passing, you would require to fulfill certain conditions. When they exactly come in line, this ring is seen, and it disappears within some microseconds or something like that. So you could calculate that. So this is a NASA image for this thing, and the way you could understand it is like, suppose if you have a candle over here, suppose if you have a glass with a flat bottom, and you sort of adjust it, sometimes you'll see the full this lightened up. So that is an analog of what actually goes on over here. Okay, and this is also, and so this is a more recent image of a partial Einstein ring which was formed, which is seen as the cluster Abel 370. This was, I think, from 2005 or 2006. And now comes the more important question that I was telling you in the beginning, that can we see gravity in action closer to home? That is, can we see some effects of gravity in day-to-day life? It turns out that we can. Well, I would not really call it gravity, but the basic concepts are very similar. So in a curved space, the transporting of vector may be non-trivial. We have to talk about parallel transport. And physically, this means that while transporting a vector along a curve, we'll need to keep some invariant direction with respect to a geodesic, and this is how it looks like. So when you transport a vector, keeping this vector parallel, keeping this vector the direction of the vector invariant to this geodesy. The geodesies are great circles. You come from here to here to here, the vector is changed. This is something that you see regularly in gravity, and you know that there is a very important application of this in quantum mechanics. It's called the Berry phase. It's a similar phenomenon. Okay, and this is basically, this is in flat spacetime. This is what will happen. Similarly, I just shown it for in a curved this thing. How that works. So the formula for calculating this is slightly, don't get bothered by the mathematical notation. Essentially, what I wanted to show you is that the difference between the two vectors at a given point is actually proportional to the curvature tensor that I told you earlier. If the curvature tensor is 0, then this right hand side is 0. Don't bother about what these are. But essentially, the idea is that the difference is related to the curvature of the space-time. And now the question is that if this is true, now suppose I take a gyroscope and I take the gyroscope and I go around the Earth. The Earth produces a curved space-time because the Earth is a massive gravitational object. So what should you see at the end of the day when you come back with your gyroscope? Suppose this is the Earth, you start somewhere, you come back, the gyroscope would have changed direction because you think of that vector as angular momentum vector. And in fact, in 2011, Gravity Probe B was launched by NASA to actually answer this question. Okay? And this is what the machine looked like. It's a complicated thing, so there was some gyroscope inside. And this is basically they took a path and they measured, this is actually what is known as the frame dragging formula. Okay, so they actually, so they computed this quantity and they actually found that the gyroscope had changed direction exactly as the Einstein's theory predicted. Now comes the last part. So we talked about black holes, galaxies, their formation, the metric and collapse and this and that. But in the 1970s, starting from the work of Stephen Hawking, it was realized that there's a great deal of structure, macroscopic structure associated to a black hole. That is, the black hole is actually a thermal object, it's a temperature. Okay, and don't bother about this. Stationary black holes possess what is known as constant surface gravity, and there is some notation, maybe we will not go into that. But what happens is that, suppose you have a black hole which has a mass m, some electric charge q, some angular momentum j, some angular velocity omega, some electric potential phi. What Hawking showed is that if these quantities are changed, like if you change A slightly, how would you change the area of the black hole? Well, the area of the black hole depends on its mass, the Schwarzschild radius 2m by r. So you change the mass a little bit, okay, and so that changes the area. Now the charge is changed a little bit, the potential is changed, the angular momentum is changed a little bit. It turns out that there is this thing called the surface gravity, whatever it is. Think of it as a proportionality constant. The change of the mass of the black hole is exactly like change in area plus change in charge plus change in angular momentum. Now, if you replace the mass of the black hole m with the energy E, the area and the area of the event horizon A by the entropy S, and kappa, that is the surface gravity with the temperature, this actually looks like the first of thermodynamics. dE equal to TdS plus phi dq plus omega dj. And this led, and where does this temperature come from? Well, that is actually what is known as the Hawking temperature. Hawking showed that black holes are not entirely classical. So basically, so if you consider some matter outside the black hole, so there might be pair production, some matter will fall in, something will go out. They actually show a thermal distribution with some temperature called as the Hawking temperature that exactly coincides with the surface gravity. And therefore, a black hole can also be a laboratory to understanding phenomena of thermodynamics. And this is, so classically a black hole cannot radiate, but within the realms of quantum mechanics it can. And so because it can radiate, the black hole has a temperature which is called as the Hawking temperature, and once you identify the Hawking temperature, there is one more thing to do, which is actually you need to postulate that the area of the black hole is related to the entropy. Now this is something which has been intriguing physicists for the last few decades. Usually an entropy is an extensive quantity, it should be proportional to the volume. It turns out that for black holes the entropy is proportional to the area. Why that is the case, and what are the ramifications of that, is still a subject of very popular research. So this is actually what is the proposal of Bekenstein and Hawking. So Bekenstein-Hawking proposal relates the entropy of a black hole to its area, and you say this is the Bekenstein-Hawking area law. The area of the black hole and the entropy of the black hole is related by a factor of, by a proportionality constant of 1/4. Okay, and so but now the entropy of black holes have to be, actually these are quantum in nature, because so black holes they have micro states, and so what is going on is not very clear, and it turns out that there are various aspects of black hole entropy which has still not been understood fully. One very intriguing point is that the black hole entropy seems to be ensemble dependent, whereas in usual thermodynamics that is not the case. Okay, so these are open questions which have not been answered. And understanding the quantum origin of black hole entropy may be a way to understand quantum gravity, which is still probably the most important open question that remains. So if black holes have entropy, and if black holes have temperature, and if black holes behave like thermal objects, then black holes also should exhibit phase transitions in some sense. And what has been found in the last 7, 8, 9 years is that there is a class of black holes called anti-de Sitter black holes, which arise from some constructions in string theory, which actually show some effects similar to what you see in usual thermodynamic systems, and I will just show you some graphs. I mean, if you compute the entropy of it's very, don't take this too seriously. I mean, some class of black holes, I've just plotted the entropy versus the temperature. You see that there is a first order phase transition over here. And if you actually compute the free energy, this is something that you must have seen in your thermal physics textbooks. The free energy looks like, there's this Maxwell's equal area construction. There's a swallowtail behavior, what happens in usual thermodynamic systems like boiling water and stuff like that. So we now believe that black hole phase transitions have liquid gas-like behavior, and this is what I said, that black holes also, they're related to some things that you see around you, and people have calculated critical exponents, and it turns out that these critical exponents that you calculate from these phase transitions, they show mean field values. So I'll stop over here with some conclusions. So recently, to tell you the very recent story, now the major thing about black holes is driven by string theory and the ADS-CFT, what is called as the anti-de Sitter conformal field theory correspondence. The idea of this ADS-CFT correspondence is to actually study a gravitational system and map it to a realistic condensed matter physics system. And the many mathematical aspects of black holes have still not been very well understood, and there are several open questions. And the last open question, or the final thing, is what is a quantum theory of gravity? Nobody knows what it is, but hopefully someday the answer will be found. Thank you. Okay, so questions. Sorry? Yeah, conformal field theory is actually, well, I mean, suppose if you take a metric G mu nu, and if you take another metric which is related to G mu nu by some factor which might be a function of space and time, but just a multiplicative factor. These two metrics are said to be conformally related. A quantum field theory which actually satisfies this condition is called a conformal field theory. Okay. And also there are several aspects like conformal field theory, there are some symmetries and things like that, and okay, so if you want to look at it this way, so there is a quantum field theory should satisfy a set of transformations. The usual set of transformations are your Poincare transformations, which include the Lorentz transformations, the rotations, etc. There is also something called as a conformal transformation. So if a quantum field theory satisfies all of that, that's called a conformal field theory. Yeah, so acoustic black holes, basically what happens is, so if you take a fluid system and if you do a perturbation in the fluid system, it turns out that the perturbation equation satisfies what is something like a Klein-Gordon equation. You have heard of the Klein-Gordon equation? No. So, okay, so the Klein-Gordon equation is actually the generalization of the of the Laplace equation. Okay. So basically what happens is that when you have a fluid system, a small scalar perturbation in the fluid system follows a Klein-Gordon equation, and the Klein-Gordon equation necessarily involves a spacetime metric. So you could show, one can show that the equation arising out of that perturbation looks like a Klein-Gordon equation with some metric, and that is called as the acoustic metric. And that metric also has behavior, black hole like behavior. Like in usual black holes, you have an event horizon from which light cannot come out. So for this acoustic black holes, you also have some kind of an event horizon beyond which the speed of sound becomes imaginary, something like that. Okay. Yeah, anything else? Yeah. Yeah, right. Relate that as in, okay, so the, I mean, the point is that what I showed you is that the black holes have very, thermal structures very similar to this thing. Now, it turns out that there is something in string theory called this ADS-CFT correspondence, which tells you that a gravitational system, a system of gravity can be actually mapped to a quantum field theory at strong coupling. Okay. So this, if this is because of this correspondence, what people believe is that if I have, usually what happens is when you are doing a quantum field theory, so you have something called a coupling constant in the theory. Okay, so now when the coupling constant is small, one resorts to perturbative techniques and you could solve things like QED and things like that you could solve. But if the coupling constant is large, then there is nothing that you could do. I mean, very little is known about quantum field theories where the coupling constant is large. But now with this ADS-CFT correspondence, that tells you that a theory of gravity is gravity as in a theory of weak gravity is actually equivalent to a theory of strong coupling constant in a conformal field theory. One actually can do calculations on the gravity side and map them to the other side to understand phenomena in strongly coupled systems. For example, things like superconductors and their behavior, that actually can be predicted by constructing a corresponding theory of gravity where the calculations are much simpler. So that is basically what I meant, that a theory of gravity can be used in order to understand things which you otherwise do not know. Okay, that is coming entirely from the ADS-CFT correspondence. Okay. Anything else? Yeah. Yeah. That's right. That becomes black. So we'll see. No, to the same. Yeah, absolutely. Yeah, absolutely. The second question is that event horizon and the black hole itself. So, what the size of black hole and size of event horizon, how are they? No, so actually, see, when I showed you the Schwarzschild solution, so this is basically a point mass sitting at somewhere. The size of the event horizon is measured by the magnitude of the mass. It's 2gm by c squared. That's it. Okay, so r is like 2gm by c squared. So the size of the event horizon is whatever the mass you put, whatever is the magnitude that determines the size. Now, when you talk about the size of the black hole, people roughly mean the size of the event horizon. So that is determined by what amount of mass you have inside. But this is actually just a very general idealized description of a black hole, because these are this mathematical black hole. Astrophysical black holes are accreting, and there are various things going on over there. But in reality, the usage of this is that if you have an astrophysical black hole, outside the astrophysical black hole, once you're outside the event horizon, you don't have any idea of what is inside, because no information can actually pass from outside to inside. So you could actually, model as if the whole mass was concentrated at the center, and symmetry gives you excellent results otherwise. Okay. Yeah. Right, right, right. Yeah. No, so actually what will happen is that you could write down the geodesic equations. The geodesic equations are the equations of motion of a particle. So what will happen is that the geodesic equations will show, so there can be radial geodesics, which the particle will come, fall inside and just disappear. Yeah. Not for, yeah, that's right, not for the Schwarzschild. The Schwarzschild black hole is just a point mass. But otherwise, yes, yes, yes. Yes, 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 yes. Certainly you can have, certainly you can have.